Good day everyone and welcome to another video. We are now on lesson number 5, which is the material balance on multiple units. In this lesson, you will be learning the techniques on how to solve a complicated material balance problem that involves several units. In our past lessons, we have focused on solving problems with only one unit. Okay? Let's begin. There is not much introduction in this lesson, no? I would like to focus more on problem solving or on the techniques that you need to learn on how to solve these types of problems. As a brief introduction, the material balance process for multiple units is the same as working with single units. You just have to do it many times. Oftentimes, you will be given problems that have more than 5 units, but not all of them would be useful. You just have to take a look at the problem, determine which of the units would give you the most information regarding the given and the required, and then you can solve those problems using the techniques that we have established for single units. There is only one technique in handling multiple units, and it's this. Strategically place your system boundary where there are enough given to solve the problem. In one of our previous lessons, I have mentioned that you need to place systems boundary on your diagram. We did not do that for single units because you only have a single unit. Of course, you will be considering the entire unit. But now that we are considering several units, it's important that you know how to place system boundaries. You can do it in several ways. First, you can write a system boundary on a single unit if you just want to consider that unit. Second is you can have your system boundary for 2 or more units that are adjacent with each other or are interconnected. And the third one is you can write your system boundary for the entire process. Doing so would simplify your calculations. It would also reduce your number of unknowns. So with that, let's start with a problem. So as we are solving these problems, I will be teaching you some of the techniques, no, from drawing the diagram to actually solving the problem. In this format, we would be reading the problem and at the same time, we will be drawing our diagram. Okay, so let's begin. Strict limits on the emission of acetone in processes forced you to design an absorption tower to recover acetone from a waste gas stream flowing at 1,400 kilograms per hour, containing 3% acetone, 2% water, and the remainder is air. Okay, for the first unit, we have an absorption tower wherein your input, we will be calling that V1, flows at 1,400 kilograms per hour. And that contains 3% acetone. We will be representing acetone as AC, 2% water, and the remainder, which is 95%, that's air. Next, water is used as the absorbent. This is our absorbent. We will be calling that L1. It contains water. Water is used as the absorbent, which is fed to a distillation column after absorbing acetone. So the liquid effluent from the absorption tower will be fed to a distillation column. So this is our L2, wherein we have a distillates and a product. The gas stream leaving the absorption tower contains 0.5% water and no acetone. The gas leaving the absorption tower is the V2. It contains 0.5% water. The remainder, 99.5%, is air because there's no acetone. Okay. The liquid effluent containing 19% acetone. The liquid effluent in an absorption process is L2. So this stated contains 19% acetone. The balance being water, so that is 81% water. So that is fed to the distillation column, and that is distilled to give a distillate of 99% acetone. The balance, of course, is water. And a bottoms with 4% acetone. Sorry, this should be bottoms. 4% acetone. The balance, 96% is water. Okay, that is our entire process. Now, take note that we have two units here, the absorption tower and the distillation column. You are used to just solving for one, okay? So what are our required? Calculate the composition and flow rates of all unknown streams. What are our unknown streams? We are only given V1, so the unknowns are V2, L1, L2, distillate, and the bottoms. We also need their compositions. We are also asked to get the percent recovery. Presumably, we will be getting the percent recovery of acetone because that is the one that we are concerned about here. We also want to determine the amount of water used per kilogram of recovered acetone. The amount of water being used is L1 because that is our absorbent. And the recovered acetone is in the distillate because if you take a look at the distillation column, the one with the highest concentration of acetone is our main products, and the other one is just a waste or a byproduct. Therefore, the amount of recovered acetone would be the amount of acetone in distillate. So the acetone in distillate. Let's use asterisks here. And then last one, percent loss of water through air. Okay, let's begin solving this problem. I will be removing this first. Let's first set our basis. The basis in this case would be based on the flow rate given, that's 1,400 kilograms per hour. Therefore, a basis of 1 hour operation is optimal. After setting that, we can now proceed with our solution. Now, your solution here is quite different from previous problems because you can, from our previous problems, you can go straight with the conduct of the OMB and the component balances. In this case, you still have to set your system boundary. The system boundary could either be just the absorption tower or just the distillation column or a combination of both, and we call that the overall boundary. So let's start with the overall boundary. Let's see if we can get some useful equations. So I will be denoting the overall boundary with red. This is our overall boundary. Now, whenever you are performing balances on a boundary, you have to take note of which streams are going in and going out of the boundary. The streams that are not crossing the boundary should not be included in the equation. For example, if you take a look at stream L2 or the liquid effluent of the absorption tower, it does not originate from outside of the boundary. It also does not cross the boundary. So it's not included in our solution. The only streams that are going in of the boundary are L1 and V1, and the only streams that are going out are V2, D, and B. Okay? So your OMB would be V1 plus L1 is equal to V2 plus D plus B. We're given the value of V1, 1,400. So substitute that. We now have our equation 1. So we have 4 unknowns in this equation. We have to look for other equations before we can solve this one. Next, in our previous lessons, I have always reiterated that the easiest way for solving a material balance problem is looking for a tie component, if any, and that allows us to simplify our calculations. So looking at this problem, we do have a tie first and foremost, we only have 3 components in this problem: your acetone, your water, and air. If you take a look at acetone, it's not a tie component because it exits in multiple streams, that is in your distillate and in your bottoms. If you take a look at water, it's also not a tie component. It also exits at the distillate and the bottoms. And if you take a look at air, it enters at V1 and exits at V2 only. So it's your tie component. So let's perform our air balance. What would be your air balance? That is 95% of V1, which is 1400, is equal to 99.5% of V2. So coming from this equation, we can now solve for V2. That is 0.95 of 1400 divided by 0.995. V2 is 1336.68 kilograms per hour. So we will not be using significant figures yet, okay? Let's just first collect all of the unknown values. Okay, next. We now have performed the tie component balance. Let's now consider one of the other components. So we can use acetone. Let's use acetone. You might be wondering, why did I choose acetone balance over water balance? We have one main reason. If you take a look at acetone, it's involved in a less number of streams. So acetone comes in at V1 and only exits at D and B. So that's only 3 streams. If you take a look at water, water enters in V1 and L1 and it exits in all streams V2, D, and B. So you have there 5 terms. Okay? We need to choose the balances that would give us the least amount of terms for easier solving. So our acetone balance would be 3% of V1, which is 1400. There's no acetone in L1. So equals 99% of D plus 4% of the bottoms product. That is our equation number 2. We now have 2 equations, but we cannot solve them yet because in equation number 1, we still have the unknown for L1. Okay? We now have reached the limit of our component balances because remember, if you perform a water balance and solve those 3 equations simultaneously, that would give you an infinitely many solutions. So that would not give us our final answer. What we need to do now is to section off another portion of our diagram. It could either be the absorption tower or the distillation column in order for us to solve for another variable. Let's try that. This is where the sectioning of your process is very important. You have a decision to make here. Do we section out the absorption tower or do we section out the distillation column? Okay, we have pros and cons for those 2 choices. First, for the absorption tower, if you're going to section that off, your main advantage is you already have 2 variables that are known in that process. That is V1 and V2. V1 is given and we were able to solve for V2. We just need to solve then for L1 and L2. That is your advantage if you choose the absorption tower. If you choose the distillation column, we don't know L2, we don't know distillate, we don't know bottoms, but we do know all of their concentrations. We can perform here a 2 equations, 2 unknowns solutions. Okay, but that would be tiresome. So let's try to section off the absorption tower. So I will be using a blue marker to represent our second boundary. So this is boundary number 2. This is in your absorption tower. Since we are talking of the absorption tower only, you will only be considering all of the streams that are coming in and coming out of the blue boundary. So let's perform our OMB. Our OMB for boundary number 2 is V1 plus L1 equals V2 plus L2. We know the values of V1 and V2, so we can substitute. This is 14 plus L1 equals 1336.68 plus L2. We now have another equation. We call this equation number 3, wherein we have two unknowns, that's the L1 and L2. Now, we can also perform a component balance for boundary number 2. And we cannot perform the air balance here because we have already done that, and we have already determined the value of V2. So your choice here is to perform either an acetone balance or a water balance. But seeing this, acetone balance would be simpler because it enters at V1 and it exits at L2. So let's perform the acetone balance. That's 3% of V1, 1400. That's equal to 19% of L2. We can directly solve this equation to determine the value of L2. So we have 3% of 14 divided by 0.19. L2 is 221.05 kilograms per hour. We now have L2, so you can go back to equation number 3, substitute L2, and we can get L1. In equation 3, L1 is 1336.68 plus 221.05 minus 1400. So L1 is 157.73 kilograms per hour. Okay, we now have values for L1, L2, V1, and V2. The only thing remaining is the distillate and the bottoms. If you go back to equation number 1, we can now simplify that equation. In equation number 1, what do we have? 1400 plus L1, 157.73 minus V2. V2 is 1336.68. Therefore, we have 221.05. Therefore, your equation 1 simplifies to 221.05 is equal to distillate plus bottoms. We will call this equation number 4. Now, it's not a coincidence that your equation number 4, which was derived from equation number 1, looks like your overall material balance for the distillation column. Take a look. For the distillation column, what is your OMB? That's L2 equals D plus B, and L2 has a value of 221.05 based from our previous calculation. So you know that your calculations are matching with each other and you are on the right track. Okay, so we now have equation number 4. We also have equation number 2, which we haven't used yet. So we have two equations, two unknowns. Your unknowns are the distillate and the bottoms. We can solve those two equations simultaneously to get both. So let X be the distillate and let Y be the bottoms. Your coefficients are, for equation number 2, that's 0.99, 0.04, and 0.03 times 1400. For equation number 4, 1, 1, and 221.05. This is your X, or this is your distillate. So the distillate is 34.90 kilograms per hour. Bottoms is Y, 186.15 kilograms per hour. We have completed the material balance. So we have determined all of the missing streams. For the compositions, we don't have to answer that because all of the compositions are already given. Some of those compositions, we just have to solve for the balance. We just have to subtract it from 100. Okay, so we're done with that. Next, the percent recovery of acetone. If you take a look at our process, acetone is being recovered in the distillates because that is our main product, and it only contains 99% acetone, while your acetone enters in V1. The percent recovery of acetone would be the amount of acetone recovered over the amount of acetone that's input to the problem. So let me first summarize all of our findings, and then let me delete some parts. Okay, here is the summary of all of our findings. Now let's try to answer the last three problems. First, percent recovery of acetone. Okay? The percent recovery of acetone would simply be the ratio between the acetone that was recovered from the distillate, which is our main product, divided by the total amount of acetone that was input to the process. So the acetone recovered is 99% of the distillate, which is 34.9, divided by the total acetone input is 3% of 1,400 times 100%. So the percent recovery would be 0.99 times 34.9 divided by 0.03 times 14. So it's 82.26%. That's our percent recovery. For significant figures, I think, let's go back to the problem. I think it's three significant figures. So it's 82.3%. Next, we need to compute the ratio L1 over the acetone in D. If we go back to the problem, we are looking for the amount of water used per kilogram of recovered acetone. Water used per recovered acetone. How much water was used? It's L1. L1 is 221.05. Recovered acetone is 99% of 34.9. We don't multiply that by 100% because I think it's asking for a ratio. $6.40. So what does 6.40 mean? This number means that 6.40 kilograms of water is used to recover 1 kilogram of acetone. So the units here is kilogram water used per kilogram acetone recovered. These types of ratio are very important in deciding whether a process is efficient or not. If you take a look at this value, 6.4 kilograms of water is a lot of water that needs to be used per kilogram of acetone that will be recovered. Okay? Next, percent loss of water. The loss of water is coming from two streams here. We have two waste streams. That's the bottoms, and that's V2. Okay? In V2, you have 0.5% water. In the bottoms, we have 96% water. So that would be your numerator, how much water is lost. Your denominator would be how much water was entered into the process. Okay? So for the numerator, 0.5% of V2. V2 is 1336.68 plus 96% of water, 96% of bottoms. Bottoms is 186.15. Divided by how much water was input, or how much water was fed into the process. Water was fed into the process through L1 and V1. So L1 is 157.73, and in V1 it's 2%. So 0.02 times 1,400 times 100%. That is the percent loss of water. Inputting in the calculator, we have 99.8%. Majority of the water is lost in the process because it exits in the bottoms and in V2, and only the 1% in the distillate is the water that is recovered. Okay? So we consider the water in the bottoms as a loss because we will not be using the bottoms products. We are interested in the distillates. Okay? So that is how you solve a multiple unit problem. This problem is an easy one because you only have 2 units. In our succeeding examples, we would have more than 2 units. Okay, let's see the next example. In the production of soybean oil, dry soybeans containing 13.5% oil and 86.5% solids are fed to a grinder where they are milled to a paste. Okay, let's first draw that. So we have a grinder, and soybeans enter with 13.5% oil. And the balance is solids, 86.5%. And of course, you are simply grinding the soybeans, so there will be no change in its composition. After it gets out of the grinder, it's still 13.5% oil. Okay? After that, the ground beans then enter a continuously stirred reaction tank together with a hexane stream, where the hexane is used to extract the oil from the ground beans. So even if it says that it enters a continuously stirred extraction tank as a unit, you can simply call it a tank because our purpose is to just mix the hexane with the ground soybeans. So hexane enters the tank at a rate of Hexane enters the extractor tank at a ratio of 3 kg hexane per kilogram of beans. So that's 3 kilograms hexane per kilogram of beans, which is the feed. The purpose of hexane here is to extract the oil from the soybeans. Okay? After extraction, the effluent of the extraction tank goes through a filter where the filter cake consists of 85% solids. So after mixing the ground soybeans with the hexane and the oil has been extracted, the effluent of the tank will be placed into a filter wherein the solid residue will be filtered out. In this case, the solid residues contain 85% solids, 14.2% hexane, and the remaining is water. So how much is left? 0.8% water. Okay, that is our residue. Next, the filter cake is discarded. The liquid filtrate then goes through a heated evaporator wherein all of the hexane evaporates, allowing pure oil to be withdrawn from the bottom of the evaporator. So after filtration, we have obtained the solid parts, which is the residue. The liquid part would then enter the evaporator, from which you will be evaporating all of the hexane. So we will be calling this H2, the evaporated hexane, and the input hexane is H1, and the product of the process is pure soybean oil. Okay, let's browse again the problem to see if our system is complete. So we have the grinder, the mixing tank, the filter, and then the evaporator. Okay, and then the problem is asking us to solve for, first, soybean oil yield, which is the amount of oil obtained over the total amount of oil present. And letter B, soybean oil loss, which is the amount of oil lost over the amount of oil recovered. Okay, we can remove this now. Let's begin by choosing our basis. If you will read the problem again, the problem did not state any volumetric flow rate or any mass flow rate or any mass of the streams. No? Therefore, you are free to choose your basis. However, you have to carefully choose which stream would you be placing your basis in. You have several choices. You can choose F, let's say for example 100 kilograms of F. You can also choose R, 100 kilograms of R, because those are the streams wherein we have composition, so we can easily identify the amounts of the components. However, it would be more appropriate if you choose F as your basis, because if you take a look at stream H1, the value of that depends on the value of F. So by specifying, for example, 100 kilograms of F, automatically, we can determine that we have 300 kilograms of H1 because a ratio of 3 kilograms of H per kilogram of F is present. Okay, so that's the power of choosing the right basis. Next, as we have done before, let's choose our system boundary. Our first system boundary here would be the entire system. I think it would be beneficial if we select the entire system, because all of the given are going out or going in of the said system. So we have our overall boundary. By the way, before we forget, you see that there are 3 streams inside of the boundary that are not considered in our calculations, but we still have to name them. So let's name this A, the output of the grinder, the output of the tank as B, and the output of the filter as C. Okay, just for clarity. Okay, moving on. For the overall boundary, let's perform the OMB. What is your OMB for the entire system? Coming in is F and H1, and coming out is R, H2, and P. We have specified the basis for the value of F, and we have subsequently solved the value of H1 coming from the basis. So we can substitute 100 plus 300 is equal to R plus H2 plus P. This is now our equation 1. Next, again, we want to simplify our process, so we have to name a tie component, or we have to find for a tie components. If you take a look at the process, your solids is your tie component because solids enters at F and it only exits at R. Okay, so let's perform a solids balance. For your solids balance, we have 0.865 of F equal to 0.85 of R. We can directly solve for the value of R, or the residue. Solving, that's 0.865 times 100 divided by 0.85. So R is 101.76 kilograms. Okay, the value of R in this case will be useful when we are considering the oil loss. That's letter B, because the only stream wherein oil is being lost is in the residue. There is a little amount of oil in the residue. I'm sorry, in the residue that should be oil. 0.8% oil, not water. So let's change that. 0.8% oil. Okay, there's no water in the process. Next, we now have the value of R. Let's see what else we can balance. We can also balance hexane. So let's try to balance hexane. hexane coming in, that's H1. H1 is 300 equals, the hexane coming out is from H2 and from the residue. In the residue, we have 14.2% hexane, so that is plus 0.142 times the residue, 101.76. Solving for H2, we have that's 300 minus 0.142 times 101.76. 285.55. Now, since we have values of R and values of H2, sorry, this should be plus. Since we have values of R and H2, we can now substitute those to equation number 1 to solve for P. So substituting H2 and R in equation 1, we have value of P that is, so F is 100, H is 300, minus R, minus H2. So our product is 12.69 kilograms. So we have determined the unknown streams at the outside of the system boundary. Now, as you have noticed, we no longer need to pursue other calculations using other boundaries. We will only be determining other boundaries, such as, let's say for example, we consider the grinder only, or we consider the filter only, if we need to solve for the values of A, B, and C. Now, based on the required, which is just oil yield and oil loss, we don't need to determine the values of A, B, and C anymore. So an overall boundary is sufficient. So that's why in many cases of these types of problems, it's almost always beneficial to pursue the overall boundary first before you go to individual units. Okay? So let's answer the required. First, oil yield. The percent oil yield would simply be the amount of oil recovered, that is the product P, 12.69 kilograms, divided by the total amount of oil that was initially present. That is the oil in F. That is 13.5% of 100, which is the feed. Times 100%, we get an oil yield of 12.69 divided by 13.5. 94%. Three significant figures. That is a high oil yield. No? If you are gathering 94% of the incoming oil, then this is a pretty efficient process. Next, oil loss. So if we are getting 94% of the oil, then what would be our oil loss? The oil loss is simply the amount of oil being lost in the process divided by the amount of oil that was recovered. So the oil lost comes from the residue, that is 0.8%, 0.008 times 101.76 divided by oil that was recovered, that was your product, 12.69. Okay, so the value of this ratio is 0.008 times 101.76 divided by 12.69. It's a small value, 0.0642. Three significant figures. What's the unit of this oil loss? Oil loss has units of kilograms oil lost per kilogram oil recovered. How do we interpret this ratio? That means that for every 1 kilogram of oil that is being recovered, you are losing 0.0642 kilograms as waste. So if we convert this to grams, this is 64.2 grams. So it's like we are saying that 64.2 grams of oil is lost for every kilogram of oil that is being recovered. For such a small value, this is actually a pretty good process. Okay, we want to maximize the oil yield in processes, and we also want to minimize the oil loss. Okay, so this is an example of a multiple unit problem that only needs one boundary, that is the overall boundary. But let's say, for example, that I want to know what is the composition of stream B. So stream B contains all of the three components, the oil, the solids, and the hexane, because it just came out from a mixing tank. So if I were to ask what is the composition of B, your next step would then be you set up your boundary in the tank itself. So this is just an example. If I were to ask for that composition, then your next step is to section off the tank as your new boundary, and then you then perform all of your other calculations such as the OMB, component balance, and etc. until you find the composition of the effluent. Okay, so that is how we perform such calculations. The technique here is reading comprehension. You really have to understand what the problem is trying to tell you. Oftentimes, these problems involve actual processes. So the problem will be narrating what happens to your raw material as it is being transformed to a product. So you really have to practice your reading comprehension. You have to understand what the story of the problem is in order for you to draw a proper diagram. Okay? Next problem. This will be our last example for this session. I do plan to have another video wherein we will have another set of examples for you to get acquainted on the process of solving these types of problems. The following describes the process of obtaining fresh water from seawater by freezing. 1,000 kilograms per hour of pre-chilled seawater containing 3.45% sodium chloride is sprayed into a flash freezer, which results in the production of pure water vapor and a slurry of ice and a more concentrated brine solution. So we start with a single process, that is a spray freezer. It's a flash freezer. The input to the flash freezer, as mentioned, is 1,000 kilograms per hour. It contains 3.45% sodium chloride. Of course, the balance of this will be water. That is 96.55% water. And then the problem stated that after going through the flash freezer, you have two products. The first is pure water. The second is brine. The pure water vapor enters a compressor that changes it to pure liquid water. So we have a compressor, and the output of the compressor is liquid water. So I will be clarifying that this is pure water vapor. The brine slurry products of the flash freezer containing 4.8% sodium chloride is filtered to remove the ice. Okay, so we filter the brine, we remove the ice, we remove the ice, and you will be left with brine. The ice enters a melter where it is joined by the condensed water vapor from the compressor and exits as pure liquid water. So after the compressor, we have a melter, and this is where the ice coming from the filter joins the liquid water. And then the product from the melter is pure water. and then the brine residue exits the filter with a final salt concentration of 6.9%. So this is 6.9% sodium chloride. Let's solve for the balances. So this is 95.2% water. And then for the final product, 93.1% water. Okay, so that is our entire process. We are to determine the flow rate of all the unknown streams. So let's first label all of the streams. Our feed is F. I will be naming our products P, the fresh water. Let's label that P1. P2 is your brine, product brine. And then we still have other streams inside. So let's name this A. I will call this B. This is C. The ice from the filter is C. So now how do we solve this? By the way, the liquid water coming out of the compressor will no longer be labeled, since that would have the same flow rate as A, because what we're doing is we are just transforming water vapor to liquid water by compressing it. So there will be no change in mass flow rate. No? There will just be a change in phase. Okay, so the required are all of the streams. So that is A, B, C, P1, and P2. Okay. We first proceed by naming our bases. In this case, we are given a flow rate of F, 1000 kilograms per hour. Therefore, we can have a basis that is 1 hour operation. Next, we name our system boundary. So let's highlight our boundary. For the past few problems, we have been using overall systems boundary for the first round of calculation. So let's do that here. I will be highlighting the entire system. Okay. So when we select the entire system as our boundary, what we are meaning is, or what we mean is, the feed is the only stream that's going in, and the streams P1 and P2 are the only streams going out. So in our overall boundary, let's have our OMB. Your OMB here would simply be F equals P1 plus P2. They are the only streams that are either going in or going out of the boundary. And we have a value of F, 1000, is equal to P1 plus P2. This is our equation number 1. Now, to solve for the values of P1 and P2, we need to perform a component balance. Do we have a tie component? Take a look at all of the components. We only have 2 components here, water and sodium chloride. The water here, it will not matter if it's in the solid, liquid, or vapor state, because we will be encountering all of those phases here. So the phase is not important. What's important is the component or the composition. So they are all just water. We only have 2 components, that's the sodium chloride and water. So we are looking for the tie component, and that is sodium chloride. It enters in F and it exits in P2. So let's have the sodium chloride balance. That would be 3.45% of the feed is equal to 6.9% of P2. We can now solve for P2. So that is 1000 times 0.0345 divided by 0.069. P2 is 500 kilograms per hour. Okay, so next, we now have a value of P2. You can substitute the value of P2 to equation 1 to solve for P1. So in equation 1, you substitute P2. We now have a value of P1, which is 500 kilograms per hour as well. So we are done with P1 and P2. Now, we are being asked for the flow rates of A, B, and C, which are all inside of the overall boundary. Therefore, you need to set another boundary or other boundaries, if needed, which would be individual units or groupings of 2 units or more. Let's first try to set for individual units. Okay, now in this case, a very good setting of your next boundary would be in the flash freezer. Why is that? If you set your boundary around the flash freezer, you actually get a lot of information. You have the value of F, you know that stream A is pure water, and you know that stream B contains 4.8% sodium chloride. So by setting your next boundary to the flash freezer alone, sodium chloride again is a tie component. So you can easily solve for A and B. Let's have the next boundary. Let's call that boundary 2. So let's again perform OMB on boundary 2. That is F equals A plus B. F is 1000. F is 1000. Substitute. We now have our equation 2. Next, I have mentioned that sodium chloride again is a tie component in the flash freezer, so let's perform that. Tie component balance, sodium chloride balance. That would be 3.45% of 1000 is equal to 4.8% of B. You can directly solve for B. So this is 1000 times 0.0345 divided by 0.048. B is 718.75 kilograms per hour. Okay, we're done with B. Next, we solve for A. So you simply substitute the value of B to equation number 2 to solve for A. So in equation 2, we can solve for A, which is simply 1000 minus 718.75. We get a value of 281.25 kilograms per hour. Okay. By the way, later on we will be consolidating all of our answers with the proper number of significant figures. Okay. Next, or last one, we need to solve for the value of C. If you take a look at stream C has 2 ends. The first end lies in the filter. The second end lies in the melter. So you can either set your boundary to the melter or to the filter. So it will not matter. You should get the same answer. But let's say that I want to set it on the filter. This is now our third boundary. So boundary 3. Let's again perform our OMB. That would be B equals C plus P2. But we now know the values of B and P2. So B is 718.75 is equal to C plus P2 is 500. You can easily solve for C. This is 218.75 kilograms per hour. So, to consolidate our answers, we only need 3 significant figures. P1 is 500. P2 also 500. A is 281. B is 719. C is 219. All are in kilograms per hour. And these are our answers. So you see here in this problem, it was necessary for us to establish 3 different boundaries, but the first boundary, which was the overall boundary, paved the way for us to solve for the other values, which are inside the overall boundary. This is how you tackle a material balance problem with multiple units. You start with your overall boundary, which would give you a rough idea on how to proceed with all of the other unknowns. Okay? The next example, or the next problem, okay, this problem is the same as one of our previous examples. So this would be number 1 in your worksheet number 4. Okay? So in worksheet number 4, we would have several items, but you start with this one as your number 1, and later on this week I will be giving the number 2 and number 3. Okay? I will be giving those items at the same time that I will be giving the other examples or other solved examples under this lesson. Okay? So that's it for this lesson. I hope you have learned something. If you have some questions or clarifications, I can be reached through Messenger anytime. And on Sunday, we will be resuming our weekly consultation through Zoom. I will be posting the details soon. Okay? Thank you for listening, and as always, keep safe.